Hey guys, today we're going to be talking about isotopes. So we want to review actually the investigation that we just completed and make sure we kind of have all the information straight about how we represent isotopes and what they actually are. So the first thing we discussed together was just the definition of an isotope. What is an isotope? So we said that atoms of the same element that have different numbers of neutrons are called isotopes. So on our pictures down here, this was our warm-up activity, and we looked at these two atoms of lithium. And remember that the circles that are colored here were the opposite of what we're used to. So the dark-colored circles were protons, and the light-colored circles were neutrons. So in this first one, we found out, okay, so there's 3 dark circles. That means that there are 3 protons here. And then over here, again, we see 3 protons. But then when we go back and actually count up the neutrons, we see 3 neutrons over here. And then on this side, 1, 2, 3, 4 neutrons over here. And so we can see how they're the same element because they both have 3 protons. But they have different numbers of neutrons. And so these would be isotopes of each other. As far as how we represent an isotope or distinguish between an isotope and just a regular old atom, there's kind of 2 representations that we can use, but they both depend on the mass number. Alright, so isotopes are always referred to by their mass number. So the first representation we have up here. And you see that it kind of uses a superscript up top and then a subscript on the bottom at the same time to represent 2 different pieces of information. So on the top, this 238 is actually the mass number for this isotope. So we could say that that's the protons plus the neutrons, right? That's what the mass number is. On the bottom, we have just the regular old atomic number. Which is the number of protons. So when I look at these 2 pieces of information, not only do I know the number of protons, but I can use the protons and the mass number to figure out how many neutrons this particular isotope would have. The second convention is this one down the bottom. Alright, so the one down the bottom is a little bit simpler because all you need to do is write out the full name of the element, put a dash, and then put in what is the mass number. So I have the mass number over on the side, the full name of the element over here. And those are our 2 conventions for representing isotopes. So let's practice really quickly. We have 2 different isotopes of boron here, so we just want to identify some things about each one. So up here, remember this is the mass number, so I know that the mass number for this particular isotope is 10. The mass number for this particular isotope is 11. And then in the middle, or on the bottom here, atomic number on each of them is 5, which makes sense because they're both boron atoms, so they should both have the same atomic number. So based on this, we can say, okay, the atomic number is 5, so there's 5 protons here. The atomic number is 5, so there's 5 protons here. If there's 5 protons, then I know I should have 5 electrons, right? Because they need to cancel each other out. And then lastly, we want to figure out the neutrons. Well, I can just say the mass number minus the protons would give me 5, so I know that there are 5 neutrons. And then I can do the same thing over here. Mass number is 11. 11 minus 5 gives me 6, and so I should have 6 neutrons over on this side. And so that's one way to look at this notation. Now let's go ahead and try and write it out with the other convention for how to distinguish between isotopes. Remember, we said that this is an atom of boron, and so we want to write out the full name boron, and then we put the mass number, which is 10. So boron 10 on this side. Again, we have boron on this side, except its mass number is 11, so this is boron 11. We can actually use all this information to fill out charts just like the ones we did for regular old atoms. So for this first example, I put the box from the periodic table at the bottom of the page so we can refer to it. I have vanadium, and we're given that it's vanadium 50. So that's telling me what isotope it is. If I want to find out the number of neutrons, for example, then I have to do a little bit of math. given my mass number. So let's first just do the easy one. All right, the easy one would be the average atomic mass, which we find just at the bottom of the slide here. So average atomic mass would be 50.942. Now, given that this is a vanadium atom, right, we look at the atomic number at the top and see that it's 23. Well, that tells me the number of protons, correct? So the number of protons for this atom would be 23, which means that the number of electrons should be 23 since they need to cancel out. So what I need to do to find the neutrons is take my mass number of 50, right? Remember, that's what that is in the symbol. And I'll subtract my 23 protons. So that leaves me with 27 neutrons, because 23 plus 27 would give me my 50. So let's move to the next one. Next one is nitrogen. For nitrogen, the symbol, we can start off just writing the name, nitrogen. We'll put our little dash, and we know that it has 7 electrons and 7 neutrons. So based on the electrons, I can actually figure out the protons by going backwards here, because electrons and protons should be the same. So I have 7 protons. Its atomic number would also be 7, because I have 7 protons, and also because it's at the top of the box. And then the average atomic mass is 14.007. So how do I figure out this mass number? Remember, mass number is just protons plus neutrons, so 7 plus 7, this would be nitrogen 14, because it's 7 plus 7. So our last one is magnesium. Okay, so we know that the symbol is magnesium 25, so obviously the element is magnesium. Its atomic number we see at the top here. Its atomic number is 12, which means that it has 12 protons, and if it has 12 protons, it should have 12 electrons because they cancel out. The average atomic mass we find at the bottom, so we just have 24.305. And then its number of neutrons I would get by taking my mass number of 25 and subtracting 12 protons. So 25 minus 12 would give me 13, and so I know that there are 13 neutrons. So this is the same process we did before, except now we just have this new information for figuring out what the mass number is, because we know that it's a certain isotope. So how do I get the average atomic mass using these isotopes? And this was one of the important things in our discussion. All right, so the average atomic mass is just the weighted average of all the naturally occurring isotopes of an element. So we saw this by just observing 10 different atoms of boron. Okay, so we looked at all 10 of these atoms, and we added a little row down here. We said this is the mass number. We said 10, 10, 11, and then it's 11 actually all the way across. So we looked at the mass number, we calculated an average of our mass numbers for just these 10 atoms. And so what we came up with when we found that average was 10.8, which was actually very, very close to the average atomic mass from the periodic table. And so this kind of proved to us that the way that the average atomic mass is calculated is just by taking the average of all the isotopes of that atom. And we say that it is a weighted average because remember that there were only 2 total here that had a mass of 10. But there were 8 total that had a mass of 11. So that's saying that the isotope with a mass of 11 is actually more common than the isotope with a mass of 10, because there's 8 of these but only 2 of these. So a weighted average is just basically accounting for the fact that one isotope happens more often than another isotope. So as far as utilizing this information that we now know, we can actually look at the average atomic mass of an atom or an element and make a prediction about what its most common isotope is. Now this doesn't necessarily have to be a perfect prediction, but it's a good way for us to kind of hypothesize about these things just based on the information we're given. So, for example, carbon. Carbon's average atomic mass is 12.0107. So what I can gather from this is that carbon has to have at least 2 isotopes because it has this funky decimal in its average atomic mass. So there has to be some number that's making that average go up to 0.0107 instead of just being 12.0000. So I know there's at least 2 isotopes. There's probably one that has 6 neutrons, and there's probably one that has 7 neutrons, because if I had one with 6 neutrons, that would be atomic mass of 12, and then if I had one with 7, that would be 13. So we could average those out and be somewhere in this ballpark of 12.0107. But what is this closer to, 12, or is it closer to 13? Obviously, it's closer to 12 because this decimal is so small. All right. So since it's closer to 12, that means the most common isotope would be carbon 12, because this number is very small. Now if I go and do the same thing for boron, boron's average atomic mass is 10.881. So since I have 5 protons, okay, this is going to be between 10 and 11, so I might either have 5 neutrons or 6 neutrons, and we saw that in our little chart on the last page. But what is the most common? The most common has to come from this number down here. And since 10.811 would round up to 11, right, it's closer to 11 than it is to 10, then the most common isotope should be the one that adds up to 11. So it would be boron 11. All right, so I hope that this was helpful for you guys as just a recap of what we've been doing. And that's all I have to say about that.